Welcome to Balco's AIA Continuing Education series. Today's AIA course is titled Creating Safe Continuity in Building Movement Joints. This course has been approved for one learning unit for health, safety, and welfare with the American Institute of Architects. Balco is part of the Engineered Building Solutions Group, a segment of CSW Industrials. The EBS group unites Balco, Medicock, SmokeGuard, and Greco. These four leading brands provide innovative, safety-focused solutions for architects, building owners, engineers, and contractors with a shared commitment to life safety by design. Balco manufactures high-performance architectural construction products for the commercial market, which includes a full line of expansion joints, egress systems, fire-stopping products, and much more. You can view our full line of building products at balcousa.com. Balco is a registered provider with the American Institute of Architects CES program. This course is approved and in compliance with AIA. This program is not intended to promote any specific construction material or method of use. At the completion of this video course, you will need to take our 10-question test and get 70% correct to receive your AIA Certificate of Completion. You will receive your certificate via email. If you are an AIA member and you provided your AIA member number, we will report your course completion to AIA CES records. Please allow for up to 10 business days to report credit to AIA. This presentation is copyrighted by Balco. Any reproduction, distribution, display, or use is prohibited without written permission. This course covers how to connect the different types of barrier joints for a contiguous system. Explore joint solutions for seismic, thermal, curtain wall, head of wall, and precast assemblies. Understand when building codes apply and when a third-party inspection is required. And review the test standards, performance criteria, and best practices for specifying joint barrier systems. Today's presentation was recorded by Steve Cooper. Steve is Vice President of Promotions and Training for Balco. Steve works directly with architects, specifiers, and distributors on product education and project specifications. With that, let's turn it over to Steve.
So buildings are connected. They create a fire barrier management strategy, and that is key for life safety. So we're going to talk pretty in depth about smoke barriers and smoke partitions, which are a bit different from each other. Acoustic reduction for the transfer and the sound from inside a structure and also from outside a structure to the inside. Fire stopping, expansion and seismic assemblies, and then environmental areas like thermal and vapor control. So contiguous joint and gap barriers happen in all kinds of structures. Buildings of many types are meant to protect us as occupants. They also provide functionality, right? We need to mitigate the harmful things while allowing the comforts and services that these buildings are designed for. All types of buildings happen to have these different kinds of opportunities in them. Schools, offices, the building on the top left there is Devon Energy Buildings. It's a 60-story building in Oklahoma. There's a vertical seal on the exterior of that structure where there's an expansion joint. And then manufacturing facilities and in lots of data centers and things like that. Warehousing where there's distribution, entertainment facilities, football stadiums and arenas and civic centers and things of that nature. Transportation, so parking garages or airports and things of that nature. In the top right picture there is a design schematic of what is generally referred to as a Texas wrap, where a parking garage is stored inside a perimeter structure that is made for residential and commercial use. Housing, multifamily housing, things of that nature, dining, restaurants, all types, and then hospitals. The bottom two pictures are of UC San Diego telemedicine building that has expansion joints all the way around. So the right-hand side is a big picture, of the elevation of the structure, and the left-hand picture is a picture of where the expansion joint is located. It's pretty well hidden behind the structure, but that's where all the seismic relief happens in that structure. So those are just examples of the many types of buildings that we'll be addressing. So linear joints are designed to allow movement for thermal expansion and contraction, seismic movement, structural loads, wind sway, hurricanes move buildings, earthquakes move buildings, hot and cold temperature moves buildings. And when they move, you have to put joints in there to allow for all these different elements that are happening and putting pressure on your structure. And so when you have an opening in one of those, you need to make sure you have contained that by good measures of smoke control, acoustic transmission, fire resistance, and all the different environmental concerns. So major design elements, they include fire-rated floors made of concrete or wood, walls made of gypsum or block. There's roofing materials, exterior cladding materials. There's all different types of materials that come together to create an architectural structure. And so the joints happen in those routinely and are identified by codes and standards as head and bottom of walls. So the top and bottom of where a gypsum or block wall would meet the next floor up above it or down below it. Curtain walls, which are exterior structures that are usually on high-rise structures. Expansion, seismic, wind, and thermal control movement gaps happen all throughout the structure. So a fire-resistive joint system is required to maintain a continuous integrity of fire and smoke construction barriers in a building by implementing tested products. So that's a key component. You need to have tested products that meet the kinds of criteria that are needed, and you need to be able to incorporate the flexibility, and all of those things need to be tested so that they can reduce the impacts of earthquakes, fires, storms, noise pollution, things of that nature, UV rays, harmful elements on the structure. So containment, compartmentation is a very, very key concept in management of joint systems. When you design a structure as an architect or engineer, you compartmentalize the structure internally so that you have a way of containing the spread of any kind of issue such as fire or smoke we'll use in this particular application. And the building on the left is the MGM Grand Hotel Casino in Las Vegas. It was early 1980s. That structure had some gaps in it that allowed a lot of smoke to mitigate throughout the structure. The fire was down at the bottom, but the smoke is what made its way through the structure, and you can see that it just went through the entire structure as it went up. That's been a pretty heavily studied project over the years, but a good contrast to that is a building to the right. This is a structure. This is a chemical manufacturing facility in Yorkshire, England. And so what you can see is there's a few levels there. So you can see there's at least four stories of some glass filled windows there. And you can see up towards the third level, there was a fire that took place, but that fire did not spread beyond that area. What you're looking at right there is a containment. So that sort of L shape that you're seeing is really a big rectangular box that's got firewalls all the way around it. And each one of those studs that you see, those vertical members that you see in there, are smoke partitions. So the big rectangle is a fire protected design that is compartmentalized so that the whole structure is now down to small mini structures. And then within the mini structure, where you have it fire protected, are smaller smoke partitions. And so that design has taken place, and building codes and all that test standards are designed towards that kind of concept now. And so the items that we're going to look at are the ones that are used to help do this kind of compartmentation. So the joints that happen in that compartmentalized area consist of what head of wall applications, curtain wall applications, control joints, expansion joints, seismic joints, and environmental protective joints, which would be openings in the exterior of a structure that are designed for movement. And so we'll look at all these in detail as we move through here. So again, smoke is one of the main items that are very important to be able to contain in a structure. And so lots of surveys have been taking place. This one is John Hall Jr. from the National Fire Protection Agency. He did a lot of studies, and he noticed that 75% of casualties that happen in a fire are caused by the smoke inhalation. It's not by heat. It's not by structural collapse. It's not by the flames. It's smoke inhalation. So how does that get to people so quickly? Well, if you think about it, smoke not only gets in your lungs, but it also stops your visibility. And so one of the things that he noticed in there was the speed that smoke travels. And the reason why smoke has some speed to it, it's not just lingering around. When you have it in a contained structure, you have different building elements, and the two elements may be side by side, and they have equalized pressure in the building, whether that's done through an HVA system or whatever. The volume of air is an equilibrium. When you start introducing a new element in there, it starts taking up volume. And while smoke doesn't seem like it takes up a lot of volume, it really does. And as smoke fills the volume, the pressure changes, and then the smoke wants to move through whatever it can. So if there's an opening like an expansion joint or a head of wall joint or any kind of gap in the structure, it wants to go through that to the other side to get equalized pressure again. And so it does that. How does it do it? Well, it moves through any opening that it can find, and then how fast does it move? 120 to 420 feet per minute. For most folks, that would not relate to much. So that is about 3 to 5 miles an hour. So a 3 mile an hour, if you're a treadmiller or a walker, 3 miles an hour is a decent walking pace. 5 miles an hour is a jogging pace for a lot of folks. And so that's not too bad when you're outdoor on a track or on a treadmill. But if you pile lots of people in a corridor that's meant for egress or a stairwell, that becomes impractical. And so smoke overtakes a lot of folks. So we want to contain smoke. That's very, very important. So there's a difference in the smoke control systems in a structure. There are smoke barriers and smoke partitions. And the short version is a smoke partition is designed to keep smoke inside a contained area. A smoke barrier is designed to keep smoke and fire. That word barrier is the key difference. When the word barrier is in there, this construction material is not only meant to stop smoke, but it's also meant to stop heat and flames and things of that nature. And so they are developed in the codes and standards a bit differently. A smoke barrier through the International Building Code, IBC section 709, that is addresses a standard, which is a test standard, UL 2079, and there's other standards that are similar. It carries a minimum 1 hour rating on it for fire as well as smoke. And so IBC 715.6 identifies a section within that UL 2079 standard that is called an L rating, which stands for air leakage, which is also the identifier for smoke. And so it must be less than 5 cubic feet per minute per linear foot. A smoke partition does not require the fire segment or the L rating segment. It requires a different standard, which is an IBC 710, which refers to ASTM E90 as the standard, and it really is just a containment of smoke. So it doesn't have to deal with the fire protective aspects. And so IBC 710.7 joints shall be filled with an approved material to limit the free passage of smoke. So it doesn't have to have quite the criteria of fire and that sort of thing. One of the areas where you will find joints commonly are at the head of wall and bottom of wall. And so there are different kinds of materials that are used. Some are sealants, some are foam materials, some are tapes. There's a bunch of different kinds of products that can be used in there. And so you have smoke criteria. You also have acoustic barriers. So we're going to move to the next level from smoke to an acoustic barrier, where you have to seal that to keep a sound from transferring from one area to the other. And so just think about this. Say in a hotel, right? You don't want sound transferring from room to room, from elevators or restaurants or cooking areas, transferring into rooms or different areas. Schools, right? You don't want one classroom hearing what the other classroom's talking about so much. You just don't want that kind of sound. But there are also some health areas that are important to this, and that is HIPAA violations in medical facilities. So you do not want to have two rooms next to each other where one patient in one room can hear the doctor talking to the other patient in the other room, or any type of diagnosis or any other thing like that. So it's very, very important that you control the passage of sound through structures. And so there are standards in place. The two standards that are mostly used, the STC rating, which is a sound transfer class rating. There is a measure of the number of decibel drops that you would have with any particular product. And so there's a requirement that says that as a minimum, in most cases, you would want to have from an interior structure, room to room, a decibel drop of 50 decibels from one to the other. And so if you had 100 decibels noise in one room, you would be down to 50 in another room, or if it was 80 in one room, it'd be 30 in the next room. And so that's an acceptable drop to mitigate the sound transfer. There's another standard called the OITC, which is the outdoor indoor transfer class. And so it has a different measure, but again, similar concept. You want a reduction in what you're hearing. And so picture a parking garage next to an office building, and there's clanking sounds and honking horns, and or maybe there's a highway running beside your structure, and you don't want those noise levels and that noise pollution transferring from the outside of your structure inside your structure. And those are tested to a standard ASTM E8412B, which is also contributes to LEED. So because these components generally, when they are applied to firewalls or joints in structures, they not only have an acoustic, but they also are not supposed to propagate flame. And so they have some method of self-extinguishing and things of that nature. So this is an example of the STC ratings, the sound transfer classes. And so what are acceptable levels? If you have a decibel level, when you get up around that 50 mark, right, you start being able to hear some sounds. They're very loud sounds. Of 60, you can faintly hear shouting or hammering. 70 plus would be virtually no sound transmission at all. So if you hit that 50-60 class with your ability to impede sound transfer, then you can take care of some pretty loud noises. Products that are less than that, obviously, too much sound comes through as an unacceptable level. So when we talk about the next level, so we've talked about smoke, we've talked about acoustic. When we talk about fire barriers, these are areas in the structure that keep the fire from transferring from one segment of the building to another. But when you build these structures, they can't be completely airtight and sealed off totally with the standard barrier materials, which would be the gypsum or the concrete or things of that nature. You really need to put things like sealants or foams or seals or tapes or different kinds, whatever the approved materials are in the area to allow for the building movement and things like that to happen, but at the same time stopping the fire, smoke, sound, things like that from going through those openings. So you can see in the diagram in the center of the page, there's a stud wall, gypsum wall going up to a concrete floor, which would be a corrugated concrete floor decking material. That is designed to allow that top floor level to compress down towards the floor below it and expand back up. That happens in deflection, that happens in building movement and things of that nature. So you have to have some amount of motion that's allowed. So any item that you put in to mitigate that smoke and fire has to have the flexibility to take up that deflection at the same time. And that happens at the top of the wall, that happens at the bottom of the wall as well. So this is an example of the motion. So you can see where on the left-hand side, this design where the stud wall meets the floor above it. And then you can see on the right-hand side where that has been deflected. It's been pushed down by, whatever means, whether it's loaded with, people or whether there's some motion taking place. It could be earthquake or hurricane or something. If the building's moving, then these elements start being compressed together. And so the measures that we use in developing test standards, they have some nomenclature related to them. This one is Underwriters Laboratories nomenclature. There are several others out there. But just for instance, so you understand what you're looking at, there's sort of three parts to the nomenclature. And so what I've shown is three different colors here. The HW means head of wall application. And so you know by reading this number, it's a kind of an intelligent number. You know what you're looking at. So when you are designing a building and you want to know what kind of approved system you can use, then you know that if you've got a head of wall application, you look for the HWs and it starts homing you in on options for you to use. The next is a D or an S. In this case, it shows a D, which is dynamic, which means it is designed for movement. Some joints are made for movement. Some joints are not made for movement. Some are just a space opening, and those can be used for plumbing chases and all kinds of things. But dynamic ones are completely open spaces where no materials are inside that, unless it is part of the fire design to create a linear joint that has a fire resistive material in it. And then the rest of it is just a sequential number based on the number of tests that have been done. And so each manufacturer gets, whatever number it is that they have in line for the test that they did to an HWD design. There are some measures used in that numbering system to help you identify how big these gaps are. So, the 0 series is less than 2 inches. The 1000s are 2 to 6. 2000s, 6 inches, and so on and so on. And then the 4000 and higher are very, very large seismic gap openings of 24 inches or greater. So that just shows you what the final listing would look like on an underwriter's laboratory listed assembly, which would be the wall and the fire protection materials and all those things there together. It gives you a bunch of data that is pointed out in the schematics there that tell you what the floor material is made of and what the fire protective materials are made of and what the gypsum or whatever the other materials are designed for. And it gives you all the detail level in that listing. Curtain walls, which are the exterior structure. So it's attached to the edges of the slab and it's on the exterior of the structure, and it goes the full height of the building from wherever the curtain wall starts at the lower levels all the way up to the roof line. In between the edge of the curtain wall, which is attached to the edge of the structure, and the concrete that would be making up each floor level is a gap. That gap is allowed in there because you need to have some room for deflection. So if wind blows across the curtain wall, that can deflect in and out. So you've got movement, and it can vary from top to bottom. It can vary in different amounts across the width and the length and the height and all that. So that gap, though, has to be contained. So you cannot just have a gap between the concrete and the curtain wall, because that would allow all of these things, flames, heat, smoke, acoustics, all that would transfer through there. So those are typically filled with some fire protective material. In the picture on the right, it's a mineral wool and some type of sealant applied to the top of it, which would be the mineral wool, would be kind of the yellowish looking material there, and then the white on top of that would be some type of sealant. There are other methods of doing the same thing. So one of the things that we see is we have common intersections that happen where you have these different building elements that meet each other at the same time. We also have control joints in a structure. So control joints are like expansion joints. The difference is an expansion joint is a complete structural separation, whereas a control joint is a gap to control really cracking of building materials, like where you would have settling of a building or something like that. So these gaps are generally much smaller, but they're still significant, and they can still allow the passage of smoke and fire and flame, sound and heat and all those sorts of things like that. But they typically have very, very minimal amounts of movement. So these gaps are typically less than an inch wide. Larger joints that happen in buildings are generally related to seismic and wind motion. So the ability to expand and contract is measured and set up in test standards. These gaps are drawn into the structure in what we would call a nominal joint. So on the architectural drawing, if it says it's a 2-inch gap or a 4-inch gap or 24-inch gap or whatever, it has to open and close a certain amount. So it is not a static element. It is a dynamic element. It moves back and forth So it would close to a minimum size specified, and it would open up to a maximum opening specified, and it returns back to its nominal size. And in test standards, that is cycled multiple times to make sure that the building materials can handle that kind of motion on a regular basis rather than just a one-time basis. So this takes me to a video that I'm going to show you of an actual expansion joint application in an earthquake setting. So what you're looking at is a tall atrium, which is, you can see chandeliers there in kind of an open area. There's a tall atrium in a multi-story structure. You're looking at a floor level where you can see the checkered tile there. The blue arrows are pointing to an expansion joint in the floor. So you have a concrete slab on the left-hand side where you can see where it says expansion joint cover. To the right of that, right across from where that blue arrow is pointing on the floor, is a different slab. So those are separated by a structural gap. That gap turns and runs up the wall right there where that white column is. And so there's a joint across the floor opening, and it runs up the wall vertically in the structure. And the whole point of that is to provide a structural relief. So if the building starts to move, in the case of high winds or an earthquake or something like that, this allows those concrete slabs and the gypsum walls and the steel columns so that they do not connect with each other and bang into each other during an event. So the whole stress relief function is shown here in a video for you. So you can start to see the earthquake begin now. You can see the chandeliers moving in the top. You can see that joint gap opening up. So there is an expansion joint cover system in that floor opening. There are fire-rated elements inside that floor opening and in that vertical column. So if you did not have that gap in place right there, what you would have is a lateral load of that right-hand concrete crashing into those columns. And columns are great at support from the top down, but they're not great at support from a lateral load or impact from the side, which causes columns to buckle. So that stress relief point right there is very important. So providing that stress relief keeps you structurally sound, and then filling that with a fire resistive material so that you maintain continuity of fire, smoke, sound, all those things that we mentioned allows that to keep the environment of the building intact. And that curtain that you see in the back, that gray, that happens to be an elevator or a smoke control system that's also sometimes used in the front of elevators. And so it's kind of got two things in one in that video there. So fire barriers for expansion joints, you have these designations: FF, FW, WW. FF is floor to floor, FW is floor to wall, and WW is wall to wall. So you can see in the top left picture, there's a wide open structural opening there, an expansion joint gap between two concrete slabs. And then on the bottom left, you can see these two gentlemen walking, looking down. They're looking at that gray line running in between the walking surface they're on and then the building next to it. And that is an expansion joint gap on the exterior of a structure. And on the bottom right, just as an illustration of an expansion joint going completely through a building. The thing you need to understand about expansion joints is they are a complete structural separation from the roof to the ground and from one side of the wall to the other side of the wall. And they don't always run straight. They can run in different directions. They can turn 90 degrees and change directions and do all those kinds of things. We talked a little bit about a UL listing earlier. This is what a UL listing looks like for an expansion joint cover application and an expansion joint fire rated application. So this one, instead of having an HW designation like we looked at earlier with the head of wall, this one is a floor to floor. D is also for dynamic. So this is built and designed for movement. And then it tells you what the joint size range is by looking at that number and what sequential number that is in terms of the number of tests that have taken place. These are larger seismic applications, so the joints get quite large in some of these buildings. On the top left is a picture of a building in Las Vegas where there's an expansion joint running across a wooden floor to a tile floor, up a gypsum wall and across a gypsum ceiling. Many of the times these are installed in such a way that the mechanics are hidden behind the construction surface. In this case, that mirror polished stripe you see running up the vertical and across the ceiling is really highlighting the expansion joint system, and it as a design element because they wanted it to match those mirror polished elevators. So they just wanted to enhance that look. The bottom left is a very large exterior wall expansion joint system for the San Bernardino Arrowhead Medical Center. Very large joint gap opening there. That is, you can see the size of those windows. Those panels are about 8 feet wide. And then on the bottom right picture is a base isolated structure. The bottom two are both base isolated structures. This is the police headquarters building in Christchurch, New Zealand. And so there's a joint that runs around the perimeter of the structure, and you can see two gentlemen installing an expansion joint cover plate in that application. Several different companies provide listings. So UL are the ones that we've looked at so far, but Intertech Testing Laboratory is also another one that allows for testing of expansion and seismic joint systems. So now we're going to talk about environmental barriers in expansion joint applications. And so when you separate this structure internally, you have fire and smoke control systems. When you separate the exterior walls and roof materials on a structure, those are not always fire rated. The building codes don't always require exterior walls to be fire rated. They can be both. But in some cases, it really is designed to have a requirement for weather control. And so there are designs out there that are made to be flexible and have all the movement. But in addition to all those kinds of things, they're also tested to these standards that you see here for air, water, structural, cyclic movement, UV resistance, and thermal values of R13 to R30. There can be different types. Different systems have different kinds of insulative values. It sort of depends on the material and the thickness that you apply to the structure. But a lot of times these systems are a belt and suspenders kind of an approach. So you may have an expansion joint on the exterior of a structure, or a sealant joint like you see in the top left image there. You have a brick facade where you've got a sealant joint with some backer rod in the top, and then down inside there you've got some type of system in place that might look like the system down at the bottom of the page, where you have added, instead of just doing more sealant, you may have a system that is robustly designed to handle all these air, water. They're pressurized and things of that nature to keep the outside out and the inside in. There are a lot of different ways that these are applied to the structure. Some are just thin sheets that are stopping smoke. Some have got the sort of insulative values. Some have got metal exteriors, and some have got elastomeric exteriors. So an elastomeric exterior would be something that would prevent UV and things of that nature from getting into a structure. It would stop rain and weather and that sort of thing like that. Metal covers are often used on either very large joints or joint applications on exteriors of structures where you may have a lot of metal cladding, or you may have a lot of debris anticipated. So let's say you've got hurricane force winds in an area that's got a lot of trees and shrubs and other things like that around that would be blowing in the air, or in tornado or something of that nature. So these add some extra structural elements to the joint areas in the structure. So when these systems meet up, occasionally you will have an expansion joint in a building that meets a curtain wall or a head of wall, or all these different types of things. They come together. And so they may be tested independently. They may have different building codes, but inevitably they intersect. And so what do you do when you have those kinds of applications? And so you have to look at solutions that can be provided that provide with a continuity of the structure. And so what you're seeing on the left, this is a Nashville airport, and there's an expansion joint running underneath those benches there that you see, the padded benches, and they run into the curtain wall, and they wrapped it with a column cover. And in that column cover, there's an expansion joint that runs up the vertical and then across the ceiling. You can see it in the ceiling component there as well. But these are fire rated, and so a fire barrier is placed in the joint in the floor, And then also a curtain wall fire stop material is added to the curtain wall, and inevitably right there where those tee into each other, you need a solution that allows for both of those to function properly in that application. It's important if you can have a single source that allows you to do both of these things, right? Because the expansion joint material meets the curtain wall material, and it's very beneficial if the manufacturer has the ability to analyze both materials to determine what the compatibility is between the two, so that you can get a system that has the best chance meeting all of the fire and smoke and acoustic and environmental properties all in that same location. So those are notoriously complex applications where you have curtain walls that meet expansion joint applications. So this is, before this is you got the after picture, the finished look, and now this is what it looked like making its way there. And so that same area where you had those benches, that silver plate that you see running across the floor is an expansion joint cover system that has a fire protective material below it, a fire barrier expansion joint material. And then where it meets that exterior wall, you can see where the two join each other, and you would have the perimeter joint or curtain wall fire stopping material, and those two would butt together, and then a solution is provided at that intersection so that you have continuity. You don't want to have gaps and openings. The sizes and the makeup of the two different materials can be completely different from each other, and so it's good to have a solution that allows you to tie all those things together. Something else that happens in a structure is there may be requirements for breaching a fire or smoke wall. And so if you cut an opening into one of those, you need to have a proper method for putting that back together so that it meets the standards of the fire stopping and the different kinds of requirements that are made for that particular partition, whether it's a smoke partition or a smoke barrier. You need to be able to put that together with a solution that allows for that change in direction. So you can't just put a piece of drywall on there and mud over the edge of the joint and it looks nice and neat, and all of a sudden everything's okay, because you have breached that firewall in a way that the tiny gap that you've got where you can see the L shape where the gypsum has been cut away and being replaced, that tiny gap will allow the movement of smoke through that opening, or heat as well through that opening. And so that has to be properly sealed, and it has to be done with a system that has been tested. And so in this case, it shows a system where there has been that top right diagram that you see shows a proper way to do that kind of connection, and the materials that are used and a listing number that meets all that criteria. So when you're looking at the codes and inspection criteria, there are some specific areas. The International Building Code is the one we refer to most often. International Fire Code and NFPA, the National Fire Protection Agency, they all have related codes. Most of those are synchronized so that the language in one it meets the language in the other. And so there's lots of committees and things of that nature that actually do those kinds of coordinations. Same thing with ASTM, American Society of Testing Materials, and UL, Underwriters Laboratories. They also have committees that synchronize the information so that when the criteria is set and the testing is complete, that the two say the same thing so that you don't have conflicts in the structure. And for the most part, they do quite well at pulling these together so that you have a very clear path as to what to do in the field. And so these fire resistive joint systems of all types, so whether it's a head of wall or an expansion joint or a control joint, they are tested to these standards. So the building code 715.3 references which would be ASTM E1966 or UL 2079. Those are test standards. So the code references the standards, and the standards tell you what you're supposed to do. And so what you're supposed to do in this case is you test this for, on the right-hand side, F for fire, which would be flame passing through. So if you look at that picture, you can see flame shooting up through there. That would be a failure point in a test if it happened in a given time frame. T for thermal, so it's temperature rise, so it has to keep heat, a certain amount of heat from passing through the system. And then L for air leakage, which is the passage of mostly smoke, toxic fumes, gases, things of that nature. So you have to test for all those. And it also, if it's an expansion joint application or a head of wall application, you also have to test it to movement criteria, which is you can classify it. You can say that your building is going to be subject to only thermal expansion and contraction. And so that's tested for 500 cycles at 1 cycle a minute, which is pretty slow. And then, or it could be, it's going to be subjected to high winds or hurricane speed winds. That's tested 500 cycles at 10 times that pace of thermal. And then if it's seismic, it's tested at 100 cycles at 30 times that thermal pace. So it's very, very fast. So now you're cycling this whole motion in 2 seconds. And then there's some combinations that can be done so that instead of testing all three individually, if your building has all three criteria, there's a class 4 that is a combination that it's 100 cycles at 30 cycles a minute and 400 cycles at 10 cycles a minute. And then they do the seismic. So fire-resistive joint systems in smoke barriers, right? Smoke barriers obviously require the fire rating, so they're subject to the same types of flame and heat and the L rating for smoke passage. And then the smoke partitions are only designed to stop the smoke passage. This is just a chart that shows you the sort of in a concise document the types of standards that are used for the different kinds of joints that you will see in a structure. And all except the curtain wall and perimeter joint have the same kinds of criteria, the UL 2079 or the ASTM E1966. The curtain wall and perimeter joint is a different test method, ASTM E2307. And the reason for that is because quite often that is a combination of a rated concrete floor slab and a non-rated exterior curtain wall material. And so that criteria is quite a bit different. All of the other standards for head of wall, bottom of wall, control joints, expansion, and seismic joints all have a fire rated construction to a fire rated construction. And there are different specification sections that are used in the design of these buildings. So the architectural specification sections are noted here as well. So we use a CSI master format. The head of wall and bottom wall are in the 078-400, which is the fire stopping section. Curtain wall and perimeter joints are also in that 078-400 section. And then control joints can be either in the 079 section, it's 079-200, or in the fire stop section in the 078-400. So it can be listed in either one of those. And expansion and seismic joints are in 079-500 series. You can see that the movement range is generally varies quite a lot between the different kinds of systems. Their head of wall and bottom wall can be anywhere from 0% to 15 to 100% movement. You can see curtain walls and perimeters are generally limited to only about 5 to maybe 20% movement. Control joints may be up to 25% movement. Expansion and seismic joints are commonly 50% and even up to 100% motion, and they can have multiple direction motion. So what do you do when you have something in your structure that is non-conforming and there are no test standards to meet that? Engineering judgments are usually the go-to method. So an engineering judgment is a document where either a laboratory, a professional engineer, or a manufacturer that has tested listed systems can write a document that either interpolates or extrapolates from other similar data. So it to come up with a conclusion that says this would be our best practice in the application that you have, which is non-conforming to any other kind of solution that's ever been made out there. And this is what we believe will work in your structure. And so if you wanted a test, you would probably have to go through the path, which can be quite slow and expensive, to produce a full fire rated tested specimen for your unique condition. But this happens a lot in structures, and there are similar enough applications. And generally speaking, most manufacturers that produce fire stop materials or expansion joint materials do hundreds or even thousands of these a year. But there are some governing bodies out there that help us make sure that we do a very good job of this. Not everybody is qualified to write an engineering judgment. So there are groups that have sort of classes and certifications in place to ensure that people that are writing engineering judgments are qualified. So you don't just have some person out there who has a vested interest in making sure that they get your project complete, but so would write up something that may or may not be valid. So that's why we have companies like UL and others that have programs in place that take you through a rigorous process. You have to take a test and you have to show that you have competency in this area to be writing these. And then there are guidelines that are set. The International Fire Stop Council has a published set of guidelines that state very clearly, if you do an engineering judgment, it should follow this kind of format. It should be, it should list the kinds of materials that are used. It should list the test standards that are being used. It should list examples of listings that are similar that can be referenced to create some sort of credibility in the idea that we want to apply an engineering judgment to an application. So there are paths to get there, but it is always best practice, and it is in the International Fire Stop Council's guidelines that if there is a tested listed system that can be used, that should be used first. Only if you've exhausted all options and there are no other listings related to the condition you have in your structure, then you can use an engineering judgment. That ensures that you have done everything you can to make sure you've identified and qualified your condition. Now, you also have the option of modifying your construction to meet a UL rated or any type of listed system, UL or Intertech or whoever it is, so that you know for sure that it has been a tested listed condition. But sometimes that's not practical. If you have an existing building connecting to a new building, the existing building, you may not be able to bring that to the same kinds of tested listed systems because those buildings could have been built well before current standards and codes have been in place. And so you're trying to bridge a gap between the two. That's a good example of where you might have an engineering judgment. So the relative specification sections that architects use to address these, of course, 0784 series, the 413 is penetration fire stopping, which generally gets brought into this same kind of an arena, but we're concentrating on the joints and the continuity of joints in this presentation. 078443 is for joint fire stopping, and then expansion joint control is for, there's 0795. Usually it could be 00. Usually it's 079513, and there are subsections for interior and exterior and parking garage applications. So architects, engineers, other folks, spec writing companies, they write these CSI master format specifications so that they can reference the different kinds of building codes and test standards, and also other things like material compatibility and all those sort of things like that. And so they pull all that together, and then they start making product choices that they can use to make sure that they create this continuous barrier that is fire rated, acoustically rated, smoke rated, and has environmental properties. So if you have those all tied together and you have a nice continuous segment, then your chances of having a safe solution are greatly increased, so that you don't have breaches between the different kinds of materials where you might have a curtain wall meeting an expansion joint meeting a head of wall or bottom wall, things of those natures. And then your codes and standards, if they don't address the joinery, then you've got some issues there where you're going to have to figure out what you do when you have those challenges in place. So it's best if you can go to a source that allows you to determine and navigate those kinds of things. And then, so if you have a manufacturer that can do all those things, then they can warrant that whole joinery, which provides a solution and makes it helpful and gives some peace of mind to the ownership and to anybody that would be an authority having jurisdiction in that application.
This concludes our AIA Continuing Education On-Demand presentation. On behalf of Balco and the EBS Group, thank you for your time and attention. To receive credit for this course, you'll need to complete a 10-question quiz. Simply click the test button below to get started. A passing score of 70% or higher is required. If needed, you can retake the quiz as many times as necessary to achieve a passing score. Once you pass, your AIA Certificate of Completion will be emailed to the address you provided before taking the quiz. If you're an AIA member, We'll submit your credit directly to AIA on your behalf. Please allow up to 10 business days for your credit to appear on your AIA transcript. The EBS Group offers AIA-approved courses on life safety products. Balco covers expansion joints, photoluminescent egress systems, and fire stopping. Smoke Guard focuses on fire and smoke protection solutions. And Greco offers courses on commercial architectural railings and code compliance. Scan the QR codes or visit their websites to explore all available courses. If you have any questions or would like more information on Balco, visit our website at www.balcousa.com. Thank you again for your time and interest.